All right. I was a day off on my notes, so I don't know if I'll have a basketball next time. So, if you drop a basketball, what happens?
Fall.
This is next class. It falls. And it bounces, right? How did you drop the ball? What's going to happen this way? Very good. So, do everybody see that now? Can we do it like this? Do it again. Ready?
Whoa.
Magic. And so, we'll learn about this magic in the next lecture. That was the lecture off. But this is why I needed the basketball today. Since I have a basketball today, I wanted to show you guys that. So that's something for you to look forward to. Next lecture, that was impact, which is not today's lecture. I figured you need 15, 2, and 3 before you did. Yep, we did 2 and 3 yet? We did 1 last time, and then 2 and 3 weren't in my notebook. And so we'll do that this time. Where is engineering? Working dynamics. So this is, what are we doing? Yay, that looks like what we're doing today. So, conservation of momentum to calculate. So, homework question. I forgot to add more stuff on 15.1 for your homework. So that will be due on the next homework. Hopefully no one's too sad. With everything going on Friday, I forgot. Okay, still there. Okay. And this was a top knot in book tutorial.
This is for my belt. My belt book or rows. This is for Paul.
Sorry, my password is stored. My computer, I don't know.
It's very small also. So it's like technically it is
All right, so
I'm doing number 2 today.
so what are we going to be using to solve the problem? Energy. What's the energy at the beginning?
potential energy.
It's potential energy. And so you're going to have mgh equals, what's your final state?
It's gonna be all
It's all potential, so it's 1/2 k delta x squared, and this is 1/2 k delta x is h minus 0 squared. And that should work.
That's it?
That's it.
Okay.
No, sorry, L. It's not L0.
Now that's it.
That's, I'm introducing variables we don't have. And so basically the guy's gonna fall a distance L before this, the bungee cord starts stretching, and so it's only the extra distance X minus, or H minus L is how much the cord is actually stretched.
Part B is that totally involved?
It's the same thing, it's like,
Especially the 2 my guy was 300 pounds.
I
I was like, dude, no way. Why would 300 pounds and I have like one to one
I'm the longest slow budget.
B is just force times distance. You can have two MGHs
You're like,
and
so
your betas. All right, other questions on the homework? No, because we haven't thought about. Do you want to resume this? All right, try this again. Conservation of momentum. So we're going to do the reading quiz, applications, then look at impulse momentum for a system of particles, and then conservation of linear momentum. Hope that these will go well. All right, so let's see. We are in the DB class.
you don't have to start.
Oh. So now you should be able to, oh shoot, I did that off right. All right.
I got it. Oh, sorry. Oh, this is BB first. Yeah,
Is that everybody? Good. So, all the internal forces for a system act equal to 0. 0 is good. It is easy to calculate with. So, impulse momentum analysis during the short time of interaction is shown in the picture. What do we do with the weight? Weight is a non-impulsive force. We're going to treat it. It's You got the right answer. You want to get credit.
No one will
So it's a it actually is an impulsive force, but it's so small compared to the force of the racket hitting it that we can just neglect it so that we simplifies our life.
So, but technically, A would be correct too. Technically.
Yeah. For the analysis, for reality, A is correct. For the analysis, we treat it like a non-impulsive force. Stop dealing with reality. So, when can we use this? What is this? It's a pitching machine, and so you can basically have a integral force dt, integral force dt. We know the force, we know the time, we can calculate how fast we're throwing it. And the force is going to be small during this time. The force of the weight is going to be small, so we neglect it. Does the velocity of the ball depend on the mass of the ball?
Yeah, I did. I claim this.
Yes, no, well it depends. Is the ball going to be slipping with respect to the wheels, depending on the large how? So depending on what the coefficient of friction is, it might or might not be. As long as the coefficient of friction is large enough that you're not slipping, then when it leaves, the ball's going to be going the speed of the wheels. But if it's slipping, then it does depend on the mass of the ball. So yes, if you do a bowling ball, it will probably slip, and then it won't be the same. You might break your. Here we have a large hammer. Good. What are the guys doing here?
Driving pile.
Driving piles. Why?
For a structure.
For a structure. This is for a foundation for a structure. So you basically drop a hammer and it strikes your object, and basically the momentum is transmitted. So, what does this say? The hammer rebounds with the pile velocity change from the case when the hammer doesn't rebound. Is it better to have it bounce, or is it better to have it go thud?
More like
It bounces up.
directly to the pile driver.
All this transfer.
Well, so we're talking about conservation of momentum, where we have mass times velocity before equals mass times velocity after, right? You already know this, so I don't know why I'm here. I'm here because this is your second time. And so what happens? If this bounces up, right, then its velocity is going,
Negative.
it's negative, but you have to add the velocity down plus the ending velocity of this plus the ending velocity of this will be equal to just whatever. Since the masses are all the same, the ending velocity of this plus the ending velocity of this will be equal to the velocity of this. So if this velocity bounces and it's going up, what has to be true of this? It's going to be greater or less? Greater. Right? Because this is going down. If this starts to go up, this will have to go down a lot faster. So when you add the two velocities, it still has to equal the initial velocity going down. So if this is going up, then this has to be going down faster. So you're better off if you bounce than if you just go thud.
But the distance might not be the same, right? It might be a smaller distance with the power going in. Than the,
Well, you have to. Well, this is going to eventually come back down, so it'll actually
you're saying it'll go down faster, but maybe not as far, right?
It'll probably go down as far as well. Right, it's energy. So energy, where does the energy go? If it goes thud, a lot of the energy just goes into squishing your pile. Or if it bounces, you're conserving your energy. And so where else can the energy go? Down into the friction with the soil going down. So the less energy you go between the deflection between the two, the more energy is going to be transmitted into the soil. But it's just hard to not have it bounce. So what do we do? We have to consider the weight during this process.
Yes.
During the collision, if you hit your finger with a hammer, does it matter how heavy the hammer is? The weight of the hammer? Because you can set a hammer on your finger and it doesn't hurt. But if you hit it with a hammer, it doesn't matter if you hit your finger with a hammer like this or if you hit your finger with a hammer like this. The weight of the hammer is probably not going to be significant. It's the velocity of the hammer when it hits your finger. So we can neglect weight. So basically, a system of particles. Basically, we have an external force on a certain point I, and then we also have internal forces, which keeps our system together. And basically, for every internal force, for every action, there's an equal and opposite reaction. So if we add the two, we get 0. And that's why we can sort of, the internal impulses are also equal to 0 if we integrate those internal forces over time. So basically what we have is the sum of the mass times velocity for the whole system plus the impulse from 1 to 2 is equal to the sum of the mass times velocity for the total system. So basically the sum of the mass times velocities is equal to the sum of the mass times velocities, assuming there was no impulse. So what we can do is describe a fictitious center of mass, or the center of gravity. So we can basically do velocity of the center of gravity is equal to what? It's a weighted average. No pun intended. It's a mass to that. Right? So it's a mass times the velocity. Mass times velocity, mass times velocity. So the more mass a certain particle has, the bigger it will be in your divided by the total mass. So it's a weighted average of the velocities, which we get from a weighted average of the positions. And so we can also find the center of gravity. It's the sum of the mass times your radius, or your distance, over the total mass of the system. So, what do we have here? When we hit the hammer into here, basically all we have now is an internal force. Right? We have the force of the hammer on the what's the stake? Not a pile anymore, we got a smaller scale. So this is going to be an internal force, and while it's hitting, because the Earth is not going to be much forced during that instant, the hammer force is going to be much larger than the Earth force. We can neglect it, and so then we basically can do conservation of momentum. That's conservation of linear momentum as compared to conservation of angular momentum, which is what we're going to be talking about in the future. So, when particles collide, or interact, basically impact. So we have what's an impact? Large force, short time. That's an impact. When they're going to collide, basically you have impulsive forces, so you're going to get a change of linear momentum for the particles. But when you take all of your particles together, you're going to get conservation. And so basically what we have, just like we were hitting it before, the sum of the mass of the sledgehammer times its initial velocity is equal to the sum of the mass of the sledgehammer times final velocity plus the sum of the stake's velocity times its mass. And so then basically what? So that's during impact, and then what do? How do you figure out how far it's going to go? Friction. What tool of our toolkit are we going to be using? How far is it going to go? That's a distance. We know how fast it's going after we hit it, so it's going to be a work energy problem. So initially we're going to have a collision, and then how far on the ground it's going to go is going to be a work energy problem. So sometimes you have to use multiple tools from our toolbox to actually get the answer. So, what do we have here? We have our mass, and it was happily going along. Then it goes kaboom! And what happens? A is going this way, B is going this way, and C is going that way. So we have A, B, and C, three smaller particles. How fast is C going to be going? We know, what do we know? We know each of the masses. We know its initial velocity. We know the velocity of A and B afterwards. And we also know mass of A and B. And assuming that it wasn't a nuclear explosion, so we didn't have mass created or destroyed, we can figure out what the mass of C is. So you can basically use conservation of momentum to figure out what everybody is doing after our system. So what do we have? We have conservation of momentum. So we have, initially we have our big mass, and this is going to be going at big mass times V initial. And because we have conservation of momentum, so this is linear momentum, this is going to be equal to what? We're going to have MA, MB, and MC. And so we're going to have MA, so we're going to have MABA plus MBBB plus, and then lastly, MCBC. So conservation of momentum, the linear momentum before is equal to the linear momentum after. What we didn't do last class, we had initial momentum plus what? The impulse 1 to 2 is equal to the final, but now since we're at conservation, the impulse 1 to 2 is nothing, and so we basically are ignoring that step in the process. So, what do we have? How would we solve the problem? Well, what are we looking for? We're looking for the velocity of c, which is going to have two components. How do we figure out what the components of the velocity of c are? All right, how do we get two components from a vector equation? Vectors. So, right, in the x direction, right, we set up a coordinate system. And then in the x direction, we get what? Capital M times vi equals 0. It's equal to MAVAX plus MBVBX plus MCVCX. The x component of A, the x component of B, and the x component of C. And so the total mass in our case is 100 kilograms. And its initial velocity in the x direction is, in the x direction, it's going 20. Oh, in the j direction, they tricked us. Rao. All right, so this is actually going and the initial. Okay, that's equal to 0. It's an arrow.
Because it's along your x-axis on your
I know.
diagram, so it's
But it's something is wrong. It's an arbitrary direction. Is it? Let me see. Let me look at the analysis. No, it's an arrow. So this is the actual direction it's given. It's given in the j direction.
So the first equation goes to 0, right?
And so this is times 0. And that's equal to MA, which is 20 kilograms, times VA is 50, plus 30 kilograms times what? Minus 30 meters per second, plus, what's the mass of C? 50. It's equal to 100 minus 30 minus 20, which is 50, times VCX. So we basically get VCX is equal to,
Negative.
well, its total is 100, plus it's 100 minus 20 minus 30 is going to be 50. So this we got, this is 100 minus 20 minus 30. And so VCX is equal to, it's over 50, so it's going to be minus
100.
what are we?
100 divided. Negative 100 minus.
This is not 100, this is 1,000.
1,000 minus 900, so
Minus 1,000
plus 900.
plus 900 over 50,
Negative
which is equal to what? Negative 2 meters per second. So that's in the x direction. And in the y direction, we get this equation. We'll just do it in the y direction. So now we have our 100 kilograms times 20 is equal to 20 kilograms times 50 meters per second plus 30 kilograms times minus 30 meters per second plus 50 kilograms times what?
Is 0 because that's a k direction. So
Oh, that's a k direction.
What?
didn't see that, okay.
That will be 0 there.
So this is 0 plus, that's tricky, 50 kilograms times BCY. So we basically get BCY is equal to 2,000 minus 1,000 over 50, which is equal to 20. And then lastly, in the z direction, we get 0 is equal to what? 0 is equal to 0.
30 times negative.
Plus 30 kilograms times minus 50 meters per second plus 50 kilograms times VCZ. So therefore we get that VCZ is equal to 30 meters per second. And so we basically get VC is equal to minus 2I plus 20J plus 30K meters per second. And that's immediately after the explosion, and then what would we do? Then it would be projectile motion, 3 different projectile motion problems to figure out where these pieces are going to land. So again, we did it for the system. And so we had conservation. So 2 rails cars with masses of 20 milligrams, megagrams, and 15 megagrams, and the velocity is shown. Oh no, they're going to collide! Ah! The speed of car A after the collision, if they collide, and B moves to the right with a speed of 2 meters per second. And if this happens in 5.5 seconds, how much force are we going to get? So how would we do this? For the collision, we're going to do conservation of linear momentum. And then to figure out the impulsive force, then we will have, so basically for the system, linear momentum is conserved. For one of the train cars, it's not. It's going to have a different velocity before and after. And so we'll use the principle of impulsive momentum to figure out how much force is going on in the coupling during that time. So, fortunately for us, we only have one direction to deal with now. So, what do we have? Conservation of momentum. So we have this equals this. So 2 squares equals 2 squares. We start off with what? This is going 3 meters per second, and we need to multiply it by 20 megagrams. And then this is going 1.5 meters per second. And so we have basically 15 megagrams times 1.5 meters per second. And then when we add these two together for the system, this equals to what? Well, we know that B is going to be 15 megagrams. And then where is it going? It's going to the right. And this is times 2 meters per second. And then what's left? Well, we'll assume to the right. We don't know what direction it's going. This will be 20 megagrams times what? the VA prime. This is what we don't know. We assume positive to the right, so we just assume the direction for positive. What happens if we get a negative answer? We're bad people? No, we just assumed the wrong direction. We can't do the problem in our head. That's why we need to do the math. So don't work too hard about trying to figure out what the answer is going to be before you start out. You just figure it out. So conservation of momentum. This is our linear momentum. So we're going to get 20 times 3 minus 15 times 1.5, that's equal to what? Uh-oh, we had a nuclear reaction. There we go. Equals 20 times dA prime plus 15 times 2. That's our conservation of linear momentum, which is the only momentum we know so far. And so from here we can get that VA prime is equal to, what, 20 times 3 minus 15 times 1.5. And then this one we have to take the other side, so it's minus 15 times 2, all over 20. And what's that equal to? 0.2? 0.375 meters per second. Positive or negative? Positive? I thought it was going to bounce off.
It weighs more and was going faster.
It weighs more and was going faster. So here's the moral of the story. If it weighs more, it keeps doing what it wants to do. If it weighs less, it bounces quite well. So when you're jaywalking across the street and a car hits you, what happens? You're going to bounce off. The car is basically going to keep on going. So cross at the crosswalk. So at least when the car hits you, hopefully the car is going slowly. What? You're still going to bounce off, but the car's going slower. So that's better off. Okay, so this is part A. So this was conservation of linear momentum. That's part A. What about part B? How do we do part B?
Well,
Just
for one car.
just one car. So now we go back to the previous day. So we basically have, let's say, we start off with 20 megagrams times 3 meters per second. And we add to this, what? The integral of f dt. And that's equal to what?
Final of that one.
It's 20 megagrams times our velocity, which is 0.375 meters per second. Fortunately for us, what's this integral of f dt? Well, it's asking for what? It's the average impulsive force, and so this is going to equal our f average times 0.5 seconds. So what do we get? Well, we're only in the x direction, so we basically get 30, that's 20 megagrams times 3 meters per second plus f average. It's actually going to be a minus because we're going left. We have a positive assuming to the right. And So it's minus F average times 0.5 seconds. This is equal to 20 megagrams times 0.375 meters per second. And so what do we end up with? F average is equal to 105 what? Not meganewtons. What is a newton? Kilogram meters per second. And so a megagram is how many kilograms? 1,000 kilograms. And so it's 105 kilonewtons. Tricky with these wacky units. Megagrams. Megatrons. All right. Whoops, wrong button. So now it's going to be a good time for a quiz for you guys. So tennis ball hitting the racket during a player's serve. What about the ball's weight?
I feel like I've seen this before.
All right.
Oh.
Oh. It's still not impulsive.
It's not.
Is it subject to Newton's second law?
No.
It's not considered.
It's not considered.
Yeah, it's not.
Is weight ever subject to? I don't know. Anyway, that's a trick answer. So we'll just not count that. So, during drilling, how many impulsive forces are acting on, so again, it's hard rock, not soft soil. During the drilling, how many impulses are acting on the air hammer? All right, one more person, come on. 3, 2, let's go. C, why C? The hammer hitting on the top, and then you've got rock, which is hard, pushing back up. And so the answer is 2, which is C. In soft soil is 1. But in hard rock, it's a record.
Wouldn't in soft soil, wouldn't it still be friction?
The friction is, the force of friction is going to be small compared to the hammer force.
So then what stops the
Yeah, it seems like you can just push it. Like how soft is soft soil? It's super like water.
Well, it's during the 0.01 seconds when the hammer is hitting the stake, that friction force doesn't matter much. The next 2 seconds, that friction force does matter a lot. So it's during the collision, friction force doesn't matter. After the collision, it does. All right, how are we doing on time? Free rolling ramp. Oh, it's some American.
No.
Yeah.
We can at least set this up in our remaining time. Has a weight of 120 pounds. We have an 80-pound crate slides from rest at A, 15 feet down the ramp to B. We assume we're having a smooth ramp, which means what? No friction, which means
We're happy.
we're happy, which means we can use conservation of energy. We want how far is the ramp moving when the crate slides 15 feet down the ramp, the ram to the bottom of B. So what's going to happen?
Okay, just like slide down and they
As this slides down, what's going to happen?
Ramps.
The ramp is going to have to move to the right as well, right? Because in this direction we have, what's going on in this direction?
Normal force.
We have no external forces in this direction, right?
Oh, yeah.
For the system.
Uh-huh.
So therefore we're going to have conservation of momentum going this way. Right? So if this mass goes to the left, then the block has to, or if the block goes to the left, the cart has to go to the right. And then we have the issue of this is going to be going down. How do we? And then we basically have conservation of energy to figure out, you know, how far this is going to be going down the ramp.
So in the Y direction, it's not conserved.
Momentum is not. Why is momentum not conserved in the Y direction? Because of we have gravity and
The force of the ground pushing up.
the force of the ground pushing up. So in the Y direction, the ground is going to act, and then the force of gravity is going to be acting down. And is this a short collision problem?
No.
No, so we can't neglect gravity because we have a significant amount of time this is going to happen. So, what do we have? We have a problem. See how far we can get. So, in the X direction, we have conservation of linear momentum for the system. And since we have no friction, we also have conservation of energy for your whole system. So, conservation of energy is our favorite equation. We like conservation of energy more than conservation of momentum because it's easier because the wonderful things it does. This is a scalar equation, this is a vector equation. So, conservation of energy, basically what do we have? We have mgh is equal to 1/2 MAVA squared plus 1/2 what do we want to call it? M box and box is not a crate.
It's a ramp.
It's a crate and a ramp B ramp squared. So this is MC and MR. I got that one right. So that's one of our equations we can use.
So what about the issue M? MG on MG.
What M is that?
Great.
It's the mass of, well, what goes up and down?
Okay.
Mass of the crate, right? The ramp is not going anywhere up and down, and so that is so far so good. So that's one of our equations. What do we have? In the other one, we basically, now we have to draw a picture. Because this one we can sort of figure out in our head. We start off with what? That's what we start off with. Right, it's not moving. So that's 0. And that's equal to what's going on at the end? Right? It's going to be down at the bottom. And so what are we going to have? This is going to be mass of the ramp times velocity of the ramp. And then what about the crate? Well, we're going to have a velocity down like this, right? So this is the mass of the crate. Now what is this velocity here? This is the velocity of the crate with respect to the ramp. Right? We know that the velocity of the crate with respect to the ramp is going down the slope. Now, it's not the velocity. If the ramp was fixed, then we would know the velocity of the crate. But, so this is the relative velocity is down the slope, but what else is happening? It's also going to have the mass of the crate times the velocity of the ramp. Because we know that the velocity of the crate is equal to the velocity of the ramp plus the velocity of the crate with respect to the ramp. So these two velocities together is equal to the actual velocity of the crate. Okay. So we can mathematically combine these terms if we're lucky. This one's easy. We get 0 is equal to what? Mass of the crate, velocity of the ramp. Let's see, this is in the x direction. We have conservation of momentum. So mass of the crate, velocity of the ramp, plus mass of the ramp times velocity of the ramp, plus, or actually minus, mass of the, it's the mass of the crate, velocity of the crate with respect to the ramp in the x direction. Oh. All right. So far, so good? There's chapel today. So those are your two equations, or three equations, and you can combine those all with a lot of algebra. I'll post the solution on the web.
Sleepy.